Hey guys, Mr. Letty, lesson 3 here on Plate Tectonics. We're going to finish up the unit as far as notes are concerned with this video here. You should know it's an abbreviated form of this unit. There's a lot of stuff that we really need to be in person to go over. Um, that if I try and explain stuff over video, it's going to become quite difficult. So the other earth science teachers and I kind of got together and decided that we would drop certain things um, for now. All right. So when we last left off, this is a page we're at. If you watch the review video for the quiz, I went into this page in detail, so I'm not going to spend time doing that again. So if you need help with this page, please see that other video, and let's move on. So we're going to start talking today about the layers of the Earth. Okay, so we know that the Earth is made up of different layers. You guys have all heard of this, right? So you have the core, you have the mantle, you have the crust. So those are the basic layers, but each of those are kind of broken down. But if I were to tell you that we've only been 2 miles deep in the Earth, which would basically be like not even getting through the paper layer on an onion. So how do we know about what's going on inside the Earth? Right? How do I know where these layers are? How do I know where the temperature changes? How do I know what the temperature is? Okay, so the simple answer to this question is that we use seismic or earthquake waves to help us out and to tell us things. Now, the key here is that when there's an earthquake, there's multiple types of waves. There's a primary wave, which is the first wave that comes out, which is fast, and it's what we call a compressional wave. All right, so instead of a traditional looking wave, when this moves by, it kind of goes like this. Okay, now because of that, it moves very fast through solid material only. Okay, if it hits liquid or gas, okay, the wave dissipates. Okay, so you'd never even know it was there. All right, but that wave, if you feel that, that's when you get that, hey, what's going on? You don't know it's an earthquake yet, but you know something's not right. So it doesn't feel right, but it doesn't feel like an earthquake. Then you get the secondary wave. The secondary wave is your more traditional wave that goes up and down. Okay, that's going to be your wave that is what you consider the earthquake, the violent shaking, the damage, things like that. Okay, that's going to travel through anything. All right, so that can travel through water, that can travel through gas, and obviously travels through solids. If you are really close to where the earthquake happens, which we're going to call the epicenter, okay, and that wave was moving along close to the surface of the Earth, you'd actually see the Earth start to look like the ocean. Okay, so you'd see the wave move through the land, which would be very unsettling for you to see. You would not like that. In your mind, you're very comfortable with the fact that the Earth is stable. Okay, so once it becomes unstable or it's treating you like it's unstable, that's really going to mess with you a little bit. Okay, now because we know of these two different waves, we know how fast they travel. Okay, the fact that they can only go certain ones through solid only, others through everything. We can measure differences in time between the waves arriving and all kinds of stuff that's going to help us identify what's going on, I should say. All right, moving on. So the layers that we're going to be discussing in this part of the unit, going from the inside out, is going to be the inner core, okay, which is solid iron and nickel. Okay, then you have the outer core, which is melted iron and nickel, which sounds a little weird if you think about that. Inside the melted iron and nickel, I have a big batch of solid iron and nickel. That would kind of be like an ice cube floating in the middle of your glass of water and never melting. Okay, so we'd have to try and figure out why that happens. Okay, then we're going to go into the mantle and the crust. All right, so each layer has different characteristics, okay, which I just mentioned about the inner core being solid, while the outer core is liquid. And then some layers, specifically the mantle, we break down into smaller sublayers when we're discussing it. The mantle itself is very, very large. So we break it down into different areas that we're talking about because there's different characteristics. Okay, so what we're going to do is this is page 10 of the reference table, which I'm actually going to bring up the color version of for us to look at. Okay, and I'm going to zoom in to start. Okay. Well, that's not working. There we go. All right. So now, as we're looking at this zoomed in, this little teeny corner right here, that's the center of the Earth in the middle. Okay. This is the surface of the Earth. So we have a cutaway that's kind of like 1/4. Okay. And as we go across this, you see this black part here. That's the crust. That's the entire crust. All right. So it's very, very thin compared to the rest of the Earth. All right. So you can see that this layer here, okay, gets thicker when you have mountains, thinner when we're talking about a ocean or oceanic crust. Here's the mid-Atlantic ridge right here. So that's where new crust is forming. Okay. And you could see by these arrows that that's where the magma is flowing up and creating that. All right. And on the other side here, on the other side of the Cascade Mountains, which is on the west coast, you have the trench, okay, and you have crust that's going down and melting. Okay. Now, from there, you go into what we call the asthenosphere, which is the plastic part of the mantle. Not that it's made of plastic, it's just that it behaves differently than the stiffer mantle. So think of it kind of as a solid that flows like a liquid. And the reason, excuse me, that they use plastic is think about when you heat plastic up, right? And plastic starts to get warm, you can kind of move it around, but it's still plastic. It's not a pool of melted plastic. So it's still a solid, but it kind of moves. All right. So similar to that. Then we get down here to the orange polka dot area. That's going to be your stiffer mantle. Okay, so that's not going to flow as much as the plastic mantle is. Then you have your outer core, which is your liquid, and your inner core, which is your solid, both of iron and nickel. Okay. Now, if we look over to the right part of the page here, we have density. So we start off by telling you the density of the continental and the oceanic crust. So 2.7 for the granitic, which means it's made mostly of granite, and 3.0 for the basaltic oceanic crust, made mostly of basalt. Okay, then we get into the mantle, and it's 3.4 to 5.6. 3.4 is the top part where it's kind of touching the yellow. 5.6 is further down. Then you jump at your outer core. All right, because of its composition of iron and nickel, we have a 9.9 to a 12.2. And then we have 12.8 to 13.1, the purple area for the inner core. Okay, so pretty straightforward, giving you the various layers here. All right, showing you what's going on. Now, if I want to talk about the lithosphere, okay, that's going to be a combination. So when we talked about lithospheric plates, that's a combination of the very, very top layer of the mantle, which is this brownish layer here, which is very rigid, okay, and the crust together. So those two combined are going to make up the plates, okay? Now, if we move down, you'll see next we're going to start to talk about pressure, okay? And what's key here is that this 1, 2, 3, and 4 is in millions of atmospheres. Now you'll notice from each layer we have these dotted lines going down. That's to help you identify where the boundary is between them. So if I said, what's the pressure in between the inner core and the outer core, I'd go to this boundary right here and follow that dotted line down till it hit here. And that's going to be about 3.1. All right. But that's 3.1 million atmospheres. One atmosphere is the pressure that you're used to right now. which is about 15 pounds per square inch pushing on your body. All right, so basically the weight of a column of air, 1 inch by 1 inch, right above your head going straight up is about 15 pounds. You don't even notice it because you're used to it. Okay, now basically what we're looking at there is it's 3.1 million times greater than 15 pounds per square inch. Okay, so you are not surviving being there. We don't have anything that's surviving being there. It would all be crushed. All right, that pressure is unbelievable. 3.1 million atmospheres. So basically, if you were at the surface of the Earth, we expanded the size of the atmosphere 3.1 million times. That's how much weight is going to be pushing down on you. Think about as we're coming up to summer, you go to the bottom of a pool. That's 8 feet, okay, or 6 feet or 4 feet, depending on the pool you're in. All right, and how that feels on your ears. Okay, and you're only going down a couple of feet. So imagine what it's like the further down you go. Okay, and you see this curve here. That's going to tell you the various pressures. So if I went between the stiffer mantle and the outer core, it's going to be about 1.5 million, and so on. Okay, then we're going to move down to temperature. Okay, now I'm just going to quickly move it all the way down so you can see at the bottom here we're talking about depth. So how deep into the Earth are we? In kilometers. All right, and that's 1,000, 2,000, 3,000, so on. Okay. All right, now sticking with that difference between the inner core and outer core, which was this dotted line right here. Okay, that's going to be a temperature of about 6,000, let's say 200, 6,300 degrees Celsius. That is hotter than the surface of the sun. All right, it is very, very hot. Um, so why is the inner core solid and the outer core liquid? Well, it has to do with the pressure. Okay, so you see this dotted line that's moving here that says melting point. Okay, so under normal conditions, as we go down, the melting point goes higher and higher and higher. Well, once we hit a certain depth, which is that depth between the inner and outer core, the melting point has now exceeded the temperature. So it has not melted. All right, so the inner core here is going to be solid because of that. If the pressure decreased, it would melt rapidly. All right, if we increase the pressure, this curve would move out a little bit and you'd have more or a larger solid core. All right, the fact that this happens leads to there being life on Earth. Okay, because we have this solid core of iron and nickel, iron being key, it's in the middle of all of this liquid and it's spinning very fast, which is helping generate something called our magnetic field. That magnetic field is what protects us from a lot of those bad rays we talked about from the sun. So your X-rays and your gamma rays, things like that. Okay, so that magnetic field plays a large, large part in making sure that there's life here on Earth. Okay, so you can see the temperature curve that basically as we start to go down, the temperature goes up very, very quickly and then kind of slows down the deeper we go. All right, and then you could see here we have partial melting of rock because the dotted line and the interior temperature are kind of close to each other. So they're right on that edge. And then once we get into the mantle itself, the stiffer mantle, you'll see the melting point is much higher. So this is going to be more of a solid area. Okay? So that's our temperatures. And then if we ask how deep is it for these things, I go to the very bottom. So where is the border between the inner core and outer core? It's about 5,100 kilometers deep. Okay? So pretty straightforward. All right, back to our presentation. All right, so now let's talk briefly And I say briefly because you guys are going to be doing some research on this stuff to find out some of the cooler things that are going on with earthquakes. All right, and I'll give you some highlights of some earthquakes that have happened, but let's just quickly talk about what are they. So an earthquake is basically just the release of energy. Oftentimes it's very violent, all right, and that occurs when two plates are moving past each other. Doesn't matter if we're talking about side to side, up and down, okay, um, doesn't matter. All right. That energy is measured on something called a Richter scale. This is a number you've all heard of. So you'll watch the news and they'll say, in Los Angeles today, there was a 3.0 magnitude earthquake. Well, that's on something called the Richter scale. And I'm going to help you understand what that means. Okay. So similar to, let's move me out of the way again. All right. So similar to some of the other graphs that we looked at, the Richter scale goes up logarithmically. Sorry, got caught up in my mouth there. All right, so instead of going up by tens, it goes up by 30 each time. So if you have a 1 on the Richter scale, okay, and you compare that earthquake to a 2 is 30 times stronger than a 1. And a 3 is 30 times stronger than a 2, which means a 3 is 30 times 30 times stronger than a 1. Okay, and so on. So as you get higher up, the amount of energy being released is growing at an exponential rate. All right, it's very, very, very powerful when you get into the higher numbers. This is compared to something we call the Mercalli scale, which we're just going to talk about very quickly here. That doesn't measure energy, that measures damage. Okay, so that goes from 1 through 12 in Roman numerals. A 12 on the Mercalli scale is total damage, and then it's based on things like saying, okay, at a 5, chimneys are going to start to crack, and plaster will fall off the walls. At a 3, it feels like a truck is driving by your house. Okay, so that's more subjective. I don't like that one because it's open for interpretation. Plus, it also depends on how well constructed the buildings are. So it doesn't really, if you say, okay, there was a 12 100 years ago compared to now, that doesn't really give you a sense of what it is because the construction methods now are so much greater. All right, back here. So, moving me again. You think I just learned to make sure that the writing was not where I'm supposed to be? All right, so worst earthquake in the United States. I'm going to break this down by two ways. The strongest earthquake we've had in the United States, which is the first one, happened in 1964, which is not that long ago. It was a 99.2 on the Richter scale, which is the second most powerful earthquake ever recorded in history. Okay, and this happened off the coast of Anchorage, Alaska. This, because it happened in the water, generated some tsunami activity. Okay, we're lucky it wasn't on land because this is a ridiculous amount of energy being released. Now compare that to the most damage done, which is the San Francisco earthquake of 1906. Okay, it was a 7.8, so not quite as strong. However, because it happened on land, 3,000 people die. 80% of the city is destroyed. Okay, I want you to think about that for a second. If you had 10 buildings, 8 of them were knocked down. Okay, so that was really, really, really bad. All right. Why do you think that happened? Well, again, we're looking at slightly more than 100 years ago. Most of the city was built with wood. That is not what we build cities out of now. All right, so we're using steel. When we look at the walls, you're still using metal for the studs compared to in your house, you use 2x4. So we use wood construction for your homes. We don't do that in cities. Okay, so if that happened today, you are talking about something that would have cost the United States $400 billion, okay, in damage. That is quite a lot of damage. All right. So let's jump to volcanoes. Okay, so what are volcanoes? It's basically a mountain that has lava coming out. All right, now that could be a gentle flow, like some of the volcanoes in Hawaii, or that could be something that's very, very violent, which we're going to hear about a couple of those. All right, so we talked about subduction zones. All right, so think about that. We have one layer going underneath another layer. As that layer is going underneath, it's scraping against it, which is generating heat, which is melting some of that rock, which is turning that into magma. Okay. And as that starts to turn into magma, that magma gathers. It's something we call the magma chamber. And above, remember I said when you have the two layers that hit each other, you get these wrinkles, which are going to be your mountains. And then you're going to have the magma underneath. And that magma is under pressure. So it's going to start to move up looking for ways to get out. And that's going to have to do with where's the least amount of pressure for it to go. Okay. And you basically have a volcano. All right. Once the pressure reaches a point where the rock can't hold it anymore, it's going to flow. All right. Three that we'll talk about very quickly. You've heard of two of them. One of them I don't know if you've heard of before. So Mount Vesuvius. You know this better as Pompeii. Okay. So this happened in Italy. Okay. Instead of getting a lot of lava, you had what we call a pyroclastic flow, which is a lot of hot ash mixed with steam. And when I say hot ash, we're talking about ash that is reaching temperatures of thousands of degrees. Okay, so it basically fell, and it didn't fall like a gentle snow where it slowly built up and they got to sit there and go, oh, look, the ash is building up. It looks beautiful. This is a lot of ash that fell very rapidly and buried people in their sleep. By the time they realized stuff was going on, it was way too late. And as this hot ash is hitting you, if you get burned, what's your first reaction? Okay, your first reaction is to breathe in. So something happens, you're going to be like, well, when you do that and you're being surrounded by hot ash, you're inhaling ash that is thousands of degrees. So not only were they getting burned on the outside, they started to get burned from the inside out. Okay, so these people suffered a horrible, horrible death. All right, last eruption happened in the continental United States. I say continental because I'm not including Hawaii or Alaska in that. This happened in Washington State. Okay, we've talked about this a little bit. When this eruption happened, okay, you had ash falling down here on the opposite side of the country. It lowered temperatures for a couple of weeks because of the ash that was in the sky blocking the sun. And Mount St. Helens lost about 2,000 feet of mountain in a very violent explosion. Okay, however, nothing compared to the third one, Krakatoa. All right, Krakatoa is in Indonesia. Okay, it actually within the last few weeks just erupted again, but it was not nowhere near uh, what it was when it first erupted. Okay, 1883. It erupts with the force of 13,000 atomic bombs. Okay, um, just look and see if you can find a video that's going to show you what the devastation was caused by one atomic bomb in Hiroshima or Nagasaki, and then this 13,000 times stronger than that. Okay? It's alleged to have been the loudest event that has ever happened on Earth. All right, so for those of you who understand geography, you have Indonesia, which is over by Australia. Okay, you had this eruption, and you could hear it on the east coast of Africa. Okay, that means that the noise traveled halfway around the Earth. Okay, that's almost 5,000 miles away. That's a large distance, which that would mean if you were anywhere near that when it happened, chances are you went deaf from the hearing damage. Okay, so very, very major eruption. Can't even imagine the amount of power that it took. Luckily, it was on an isolated island at a time where the population wasn't that great. Indonesia now has a large population, which that could have been a problem if that happened today. Okay. And then finally, tsunami. Okay. So tsunami, what does it mean? It is Japanese for harbor wave. Okay. Uh, the way I want you to think about it is think about when you drop a rock in water, you get those rings that come out. Okay. Each ring is part of the tsunami. All right. And the rock that you're dropping represents something disturbing the water. So it could be an earthquake underneath. So you suddenly have the land drop. So the water rushes down to fill up that spot and then rebounds up, and you get these rings coming out. Okay. It could be a lot of debris falling into the ocean at one time. Okay. Which it hits and then pushes out the rings, very similar to you throwing a rock. Okay. Now, this would be something that potentially would save your life to understand this. Okay, because there are many examples, and you'll find when you're doing your research videos where you'll see people who don't heed this advice. People who probably, in any other sense of the word, are fairly intelligent people, and they do something unbelievably stupid. Okay, if you find yourself at the beach and the water goes away, meaning the water gets pulled back out away from the beach. This is not the time for you to be fascinated by all the seashells you suddenly see and walk out to go look at them. Literally, if you do that, that is the last mistake you are ever going to make. Okay? What's happening is that water is getting pulled out to build up the tsunami wave that's coming back in. Okay, so for that big wall of water that you see here, that water all had to come from someplace. Okay, so it would be pulling the water away from the beach. If you see that happening, you need to get someplace high quickly. Okay, tsunamis travel at a very, very fast pace. Okay, so some famous tsunamis. July 9th, 1958, we had an earthquake. 30 million cubic feet of rock high above Latuyo Bay in Alaska hit the bay, and it generated a tsunami wave that was 1,700 feet high. All right. That is quite high. 1,700 feet is putting that somewhere around a third of a mile. So if you took the track, which is a quarter mile, and made it a straight line and stood that straight up, it's a little bit higher than that. Okay. Then we have two recent ones. December 26, 2004, Sumatra, which is over in Indonesia. Okay. Undersea earthquake happens. This is a resort area. There are a lot of people who are coming from Europe who stay there. But because you're in Indonesia, they don't have early warning systems in place. All right. So when the tsunami hits, because it hit relatively early in the morning, it killed over 230,000 people. All right. So most of those drowned, and a large percentage of those people never found. So the wave came in, killed these people, and when the water receded, it took them with it. Okay. Move ahead 7 years to March 11th, 2011. All right, we have another undersea earthquake. This one happens off the coast of Japan. Only kills 15,000 people, which I know I just said only 15,000, but that's when you compare it to 230,000. Okay, that's with an early warning system. So it still killed 15,000 people. The biggest problem here is it damages the Fukushima nuclear power plant, which releases nuclear material into the Pacific Ocean that took years for it to stop. Okay, so there was a point in time not too long ago, only 5 or 6 years ago, where you should not have been eating Pacific caught salmon because you had nuclear material that entered the Pacific Ocean. And I know you're saying, but it's Japan, that's the other side of the world. But the ocean currents carried that material around the ocean. Okay? So, there are three things: tsunami, volcano, and earthquakes. You guys are going to be researching them next week. More to follow on that. And that wraps up our notes for this unit. Okay, so we'll talk to you guys soon. Thanks.